Hello grade 10s and welcome to another lesson. Today we're going to be looking at number patterns. Now one of the things about number patterns is it's really all that mathematics is based on. Everything from your grade 1 year or even your grade R year in many of your cases has been based on how to analyze what is happening to numbers. Let's take a look. Now I'm sure you've seen a puzzle like this one before. 8 becomes 56, 7 becomes 42, 6 becomes 30. So what does the next one become? Why don't you take a minute and try and figure it out? Now we actually found this number pattern on a social media network, and so you've probably come across it before. Were you able to get the answer? Did you discuss it with your friends? And this is part of the process with mathematics, is looking at how does one number become another number, and can that pattern be replicated? In other words, can you repeat it to another number? Let's take a look at what the answer is. So we have 8 and something is done to it to become 56. Now, we could have either added a number or we could have multiplied a number. And I like the multiplying because it's more simple. And maths is all about making it simple for yourself. Now the 7 became 42. And if I want to carry on the pattern that happened in the first one, I need to multiply this by something. What multiplied by 7 gives us 42? Well, that's going to be 6. Let's see if this pattern continues. For the next line, we have 6 multiplied by what is going to give us 30. Now, if our pattern's correct, we've got 7 multiplied by 8 gives us 56. 7 multiplied by 6 gives us 42. So it should be 6 multiplied by 5. Does it work? Yes, it does. So that means with the last one, we're going to have 4 multiplied by something. And I hope you realized that it would be multiplied by 3. Why? Because we're always multiplying by the number that's below it. And that's equals to 12. So there we go. If we wanted to put this into an algebraic form, we could describe the number as a variable. So let's say 8 is equals to x, and then the number it's being multiplied by we would describe in relation to it. So because 7 is 1 less than 8, we would say 7 is x minus 1. So our pattern would be x times by, in brackets, x minus 1 would give us the answer. But sometimes putting x's into things like this takes a bit of the fun out of it. Now, in maths, we find number patterns everywhere, but all of those numbers came from a place to begin with. If you've got a bit of spare time, I'd like to encourage you to look for patterns in life and see the numbers that are there. Like, how many days are there in a season? Is this true for all the seasons? Are the same number of days in winter as there are in summer? And what are the defining characteristics between those? Also, number of hours in a day. Is there some kind of rhythm in that? And girls, we can all talk about our cycles and the number patterns that happen over there. Well, on to more pleasant things like mathematics. Let's see what the next slide has in store for us. And for this slide, you need to discuss four different terminologies. We have difference, ratio, term number, and term value. And I want you to look at the person who's next to you and just discuss these four different terms. Take a look at them again and discuss that for the next minute. I hope that went well. Did you make a new friend? Probably not, because you're sitting next to your classmates and you like them already, don't you? So let's go through the different terms and see how your definitions compare with my understanding of what it is. The first thing we're going to talk about is the difference. Now, if I ask you, what is the difference between this and this, you're going to tell me the one is my left hand and the other is my right hand. I'll tell you I don't know which one's which, and then pick up a pen and go, okay, this must be my right hand. But other than that, you're going to notice each has 5 fingers, but they're opposite. Now, with difference in number patterns or difference in numbers, we're looking at what's the same and what is different about the numbers. And generally, we're talking about the distance between the numbers on the number line. So the difference between 1 on the number line and 4 on a number line is 3 spaces. So the difference between them is 3. To find the difference, we need to do a subtraction problem. 4 minus 3 is 4 minus 1 will be equal to 3. Okay, the next word we're going to discuss is ratio. Let's take a look. Now, ratio is a lovely word. It reminds me of the word relationship. I don't know why, but it does. And it helps me to remember what it means, because a ratio is a relationship between 2 numbers. Let's say the relationship between 3 is to 4. Now, this can also be written as a fraction. 3 divided by 4. So ratios can be written as fractions and ratios. And if you look very carefully, you might see the divide sign over there, which changes it into the fraction. So the ratio is the amount that one number needs to be multiplied by to get another number. So if we go back to our previous slide, we see that 8 needed to be multiplied by 7 to get to 56. Now, the rest of this number pattern doesn't really help us with this kind of thing. But if we wanted to increase 9, let's say 90, make it more challenging, in the same ratio as the previous problem, what would we do? Well, we would multiply it by 7. What is 90 minus 7? Oh, sorry, 90 multiplied by 7. Well, I hope you can get that. Let's look at the next word. A term number. Now, if we have a number of numbers, a sequence of numbers, let's say the number pattern is 1, 3, 5. Can you guess what the next one is? I hope you said 7. we would talk about these positions as term numbers. So in the first position, we have term 1. In the second position, the term number is 2. In the third position, the term number is 3. Can you guess what this position is? Let's hope all of you said 4. Now the term value is what the value is in that particular place. So let's say in term 2, our value is 3. In term 4, our value is 7. Okay, I think we now have the terminology you need to progress to the next thing. And remember that grade 10 is not so much analyzing one particular type of pattern. It's about learning the skills of analyzing all of the patterns. So I could give you a pattern made up of matchsticks, and you would have to continue it and tell me how many matchsticks I would need to make the biggest pattern, or whatever my criteria are. I could give you Smarties in a triangle shape and ask you to predict how many Smarties we would need to make the 17th term. Whatever it is, you need to use your intuition and all of the skills that you've learned up until now. And I don't just mean grade 10 skills, I mean 9, 8, 7, 6, all of them. And most of all, think. Don't think just because it's maths you're going to find the answer immediately. Go through and try each one. Try different ideas. Let's take a look. Okay, so here we have a list of all of the written definitions, and we have gone through this in quite a lot of detail. So I'm going to skip past it and look at the first question. Or not. How about this? We have a challenging question. I want you to look at this pattern of hexagons and then determine how many hexagons there will be in the 10th pattern. So that means the 10th number. There would be a 4th number, a 5th, well not number, but figure, a 4th figure, a 5th, a 6th, all the way up to 10. So how would you get that? I don't know. Let's take a look. Here's 1. But what is happening over here? What is different about these two? Anyway, I'd like you to consider that for a while. We'll come back to it. We are going to have a show at the end of the term where we go through all of these challenge questions, and I look forward to seeing what you've come up with. So, the first real question for today says, determine the general term of the following sequences and the value of the 25th term. What does general term mean? Well, general term is the algebraic way of writing something down. So I'm going to do the first one for you, just so you can see what's happening, and then we'll see what else. You can try the rest. So we have 6, we have 12, and we have 18. How did we get from 6 to 12? I think we've added 6. Let's see if this pattern continues. Yes, it does. 12 plus 6 is 18. So that means I am adding a constant difference of 6 every time. What am I adding it to? Well, the first term is 6, but the second term is 12. So maybe what I'm doing is, instead of adding 6, I'm multiplying n by 6. What is n? N is my term number. So if I were to do this in a table, let's draw one very quickly. Tables help sort out everything. Here's my n, term number 1, term number 2, term number 3, and I'm going all the way to term 25. Term number 1 was 6, term number 2 was 12, term number 3 was 18. What is the relationship between 1 and 6, and does it continue for 2 and 12? And can it be replicated again for 3 and 18? Yes, it can. It's going to be 6n. So n is equals to 1. When I substitute that in, I'm going to get an answer of 6. When n is equals to 2, 2 times 6 is 12. And 3 times 6 is 18. So our general term is going to be Tn is equals to 6n. So our 25th term then is where we substitute 25 in for n. And this little 25 at the bottom doesn't really do anything mathematically. It just tells us, and let's circle which one I'm talking about, it just tells us this is what we're going to be talking about. Okay, now, do you know what 6 times 25 is? Why don't you take out your calculator and try it out. We're going to cut to a break now, and then when we come back, we'll do some more number patterns. Hello again, welcome back. Did you have a good break? I hope you got some fresh air and you're ready to now try these number patterns. So I'm going to be a little unconventional now, and yes, we've only just said hello, but I want you to try these number patterns yourself. So I'm going to give you 3 minutes to look at the remaining 3 number patterns that we haven't done, see if you can determine what the general term is, and then find the value of the 25th term. Sometimes it's easier to find the value of the 25th term and as a result find the general term, but take a look. Okay, let's look at the slide. So the 3 number patterns I want you to try are at least B, C, and D. See if you can do them quickly in 3 minutes. So are you ready to see how you've done? Let's take a look. Now we're going to go through each question individually, and of course we've already done the first question where we found that Tn was equals to 6n. Oh, why am I putting in brackets? Let's take those brackets out. My brain is actually rushing ahead to where we needed to substitute not 35 but 25 into it, giving us, what is 6 times 25? Let's use a calculator to find that out, and I just happen to have one here with me. So 6 times by, 6 times by 25 equals 150. So the 25th term is equals to 150. But we weren't really interested in that. What we were interested in were these three problems. So let's start with this first one. Is there a common difference between 16 and 8? Well, there is a difference of 8, but the difference between 8 and 4 is only 4. So that isn't the pattern that's happening. To make this more simple for myself, I'm going to put it in a table. Why? Because tables make my life easier, and maths is all about making my life easier. So remember, the first row are the numbers of terms. My first term, in other words, term 1, is 16. My second term is 8. And my third term is 4. Is there a relationship between 16 and 8 that can be replicated to form the same bond between 8 and 4? Well, if we think about it, 16 divided by 2 is equals to 8, and 8 divided by 2 is equals to 4. So what do you think the next term will be? In other words, the fourth term. What's 4 divided by 2? It's going to be 2. What about the fifth term? What is 2 divided by 2? 1. So we can see where things are going over here. We've started with 16, we've divided by 2 and we've got 8, and we've divided by 2 again and we've got 4, and we've divided by 2 and we've got 1. So now let's go and put this into algebra. We started with 16 and we divided by 2 to get 8. Now that means that term 2 is actually equal to 16 divided by 2. Now term 3 is equals to term 2 divided by 2, right? Because it was 8 divided by 2. Now we've already said that it's going to be 16 divided by 2 as the value for term 2. So let's put that over here and then divide it by 2 again. Now I know I've made this look very, very complicated, but where I'm wanting to go with it is that we have started with a number, and I'm going to call it x. And then in the second term, we've divided x by 2. And in the third term, we've divided it by 2 again. So we've taken x, divide by 2, and divide by 2 again, which means it's divided by 4. And then we're going to divide that by 2 again and divide it, which means we're dividing it by 8. Now if you think back to your exponents, what this could be written as is x and x multiplied by a half and x multiplied by a quarter, which we know is actually a half times a half. So where I'm going with this is what we actually have is x times by a half to the power of 0 for our first term. And for our second term, we have x times by a half to the power of 1. And for our third term, we have, and let's extend the page a little, we have x to the power of a half multiplied by 2. Did you notice that each one of these exponents are one more? Now we have a fancy way of getting this right in maths. What we'd rather write is x times by 1 over 2 to the power of n minus 1. And the reason I've done n minus 1 is because, oh, and my scroll bar, there we go, because n was 1 in the first term, 2 in the second term, but when we do the exponents, it's a half to the power of 0 for the first term, and a half to the power of 1 in the second term. Okay, grade 10s. By now you're looking at me and going, where is that x coming from? I don't understand. All you're dealing with is this half, and yet we've still got 16, and you're telling me about multiplying by a quarter and multiplying by an eighth, and I really just, please, find the meaning in my life. And so I'm going to. You see, what we're multiplying by is a common ratio. And because we have a common ratio, we know that this will be multiplied all the time, and it's to the exponent power of n minus 1. What we haven't determined is the value that it is constantly being multiplied by. So what I'm going to do is try a little experiment. I'm going to put the value of the first term into this expression. So in other words, I'm going to make x equal 16. And my theory behind that is 16 multiplied by 1 is going to give me an answer of 16, so it'll work for the first term. The second term I wrote down as x times by half to the power of 1. So what is 16 times by half to the power of 1? It's 8, right? Well, let's just write it down just to make sure that we're all on the same page. So what I'm saying, and I'm just going to erase all of this over here, is that I'm going to replace all of these x's with 16. And let's see what we get. 16 to the power of, 16 times by half to the power of 0 is equals to 16. Is that term 1? Yes, it is. And 16 to the power of 1, 16 times by half to the power of 1 gives me 8. Look, we have the value of term 2. And lastly, let's just draw a little line here so that everyone can see that I'm only talking about this one. 16 times by half to the power of 2 is actually going to be 16 times by 1 over 4, which is 4. So glad you got that right. And that's term 3. So does this number pattern hold? Yes, it does, which means that our general term for this number pattern is Tn is equals to 16 times by half to the power of n minus 1. Now, in order to find the 25th term, I'm going to bring out my calculator and put it to the side and type in 16 times by, and let's put a half in brackets, and then to the, my other bracket, to the power of 25 minus 1. And let's get our answer. Wow, that's a big number. Okay, grade 10s with that. We're going to take a bit of a break. When we come back, we'll look at those other two number patterns and a lovely surprise question. See you just now. Hello again and welcome back. You might be surprised to know that those two previous number patterns are number patterns that you could expect on your matric exams. The first one is a number pattern called an arithmetic sequence, but don't worry, you'll learn more about that in matric. And the last one we did was something called a geometric sequence. Now in grade 10, we don't focus on a particular sequence or a pattern or anything. We focus more on the ability to recognize how to deal with them. And the last one, I think maybe I was a little mean by giving it to you, but it was fun, wasn't it? Okay, the next two are very closely linked. I hope you saw the link. Let's take a look at them. So, the first one, I'm going to draw a little table over here because we won't need too much space. It's actually quite an easy number pattern once you see it. So we've got term 1, term 2, term 3, term 4. And they are equal to 1, 4, 9, and oh dear, I made a mistake. That should have been 16. Well, how did I know I made a mistake? Because I intended this number pattern to be n squared. So that means 1 squared will equal 1. And 2 squared will equal 4. 3 squared will equal 9. And 4 squared will equal 16. So my error was that I skipped out 4 squared and went straight to 5 squared and put it down as 25. Oh, we all make mistakes, and unfortunately mine has now been immortalized in video, but hopefully we have learned from this. So watch out for these particular numbers. Squared number patterns and cube number patterns are favorites to be given in tests and exams. So if you know the numbers, then they're easy to recognize. Okay, for the next one, I'm going to cross out that fourth term because it no longer makes sense. And we're just going to look at the 2, the 8, and the 18, but we're going to look at it in relation to the above pattern. What do you notice about the 2 and the 1? And about the 4 and the 8? What about the 18 and the 9? Can you see that they're all being multiplied by 2? That means that our general term is Tn is equals to 2 times the previous one, which is 2n squared. Okay, grade 10s. The next part of that question would be to substitute in the value of 25 and find the final answer. You all should have a calculator near you that you can grab and plug in 25 squared, find out what the answer is, and it'll be huge. It might even involve some scientific notation. And then you'll multiply that by 2 for the other question. Shall we move on to the more interesting problems? Now, by more interesting, I mean it's going to have a picture, and I like pictures. So the next slide says, Les takes a triangle and divides it as shown. We have figure 1, figure 2. It's the same triangle, but now it's got 4 triangles inside, and figure 3. So there is 1 triangle in figure 1, 4 triangles in figure 2, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 triangles in figure 3. But what concerns me a little bit is that maybe you can't see that figure 3 is just figure 2 that's been divided up. So I'm just going to draw in those other triangles from figure 2. And can you see that each triangle has been divided by 4 again? Okay, the questions say, draw a picture what the 5th figure will look like. Sure, that'll be interesting. And B, give a formula to represent the number of triangles of the same size if expected in figure N. Now, figure N is another way of saying the general term. Okay, so you need to find the general term. And the last question says, Les wants to continue until there are exactly 1,000 small triangles of the same size. Explain why that is not possible. Okay, grade 10s. We've got it on screen, and you've got 3 minutes to try this out. On your marks, get set, go. I wonder how many of you got past drawing the triangle. It's going to take a long time to draw this image. Now, keep in mind that we need you to save time in exams. So generally, we're not going to ask you to draw something. We're rather going to ask you to apply mathematical principles. But because this isn't an exam and it's a learning experience, we're going to take a look at how to draw this. Now, I have a template based on figure 3, and I'm going to divide it up to make it look like the 5th figure. So the first figure, we divided up into 4 triangles, and then we divided each of those 4 triangles into a further 4 triangles to get figure 3. So first we change figure 3, and let's take a look at my template. This is figure 3, and I'm going to change figure 3 into what figure 4 should look like. In other words, I'm drawing in all of the new triangles for figure 4. And we weren't asked to draw in figure 4. we were actually asked to draw in figure 5. But I know the information from this drawing will help us with answering the next one. Okay. You have obviously done this with a ruler, and yours probably looks a lot prettier than mine. And I encourage you to be as pretty as possible. I'm going to stop after I've drawn this last triangle so that I can count the number of triangles in this fourth figure. Okay, let's count it. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64. 64 triangles. Sure, that was a lot of counting. Thank you for staying with me. Did you notice? Did I miss any numbers? No, it was all okay. Now, I've made an executive decision not to draw the fifth figure, but you can see how the fifth figure would be drawn. You would then divide each one of those tiny triangles up into a further 4 triangles. So how many triangles do you think will be in that one? Let's redraw the number of triangles as a table. And remember, mathematics is all about making it easier for yourself. And one of the ways we make it easier is we reduce our pictures into numbers. Remember, n is the number of the term, and I've got 4 images so far, or 4 figures, and I want to know the number of triangles. Let's look at the top one. Figure 1 had 1 triangle. So let's fill that in to our table. 1. Figure 2 was that 1 triangle divided into 4 triangles. So I now have 4 triangles. In figure 3, those 4 triangles were each divided into 4 triangles. So rather than counting it, I'm going to take these 4 and I'm going to multiply it by 4 because each one of them would contain 4 triangles. And that would give me an answer of, what is 4 times 4? Did you get an answer of 16? I hope so. Do you think the same relationship applies between that triangle of 16 and this triangle of 64? Well, we have a calculator, so let's use it to prove. What is 16 times by 4? And we're multiplying by 4 because each one of those 16 triangles was divided into 4. And yes, we get an answer of 64 triangles. So can you make a prediction about the 5th one? If you said you're going to multiply 64 by 5, or sorry, 64 by 4, that would be correct. So we're well on our way to finding out what the general term is. It's 256 over there. Because we have recognized already that the relationship is times by 4. We've got something times by 4, and then we've got times by 4, and then we've got times by 4. This reminds me of something that we've done recently. Can you remember how we show repeated multiplication? If you said exponents, you would be right. And remember, we only did that last week, so it should still be fresh in your mind. Rather than writing times 4, times 4, times 4, times 4, we're going to write times 4 to the power of whatever we've done. Okay, let me show you how. So, I'm going to make this a little easier for myself by rewriting 4 to the power as 4 to the power of 0. And then 4 as 4 to the power of 1. And 16 I'm going to rewrite as 4 to the power of 2. And I multiply that by 4 to get the next one, which is 4 to the power of 3. Is 256 4 to the power of 4? There's only one way to check, and, well, actually there are more ways to check than one, but we'll use our calculator. 4 to the power of 4 is 256. So we have our pattern. But the problem is the term number is not the same as the exponent number. Look, term 2 is not the same as that 1. And term 3 is not the same as that 2. Can you see that there is a relationship between them though? You should be able to see that it is 1 less than the term number. So that means the exponent is going to be 1 or 1 minus 1 or 2 minus 1 or 3 minus 1. In other words, it's going to be n minus 1. So that means our general term is going to be Tn is equals to 4 to the power of n minus 1. Now, I'm going to do the last question of this because we've actually done B already, which was give a formula to represent the number of triangles of the same size in figure N. And we've done that. So let's look at C. Les wants to continue until there are exactly 1,000 small triangles of the same size. Explain why this is not possible. Well, I spent a long time going through this and going, how do I show grade 10s that this is not possible without using logarithms, which is grade 12 skill? And then I remembered, you all know how to do exponents. So let's take a look quickly at the calculator. And we know that 2 to the power of 4 is 256. What would the next image be? 2 to the power of 5 is 1024. So the reason why Les can't get an image that is exactly 1,000 triangles is because there are only ones with 256 triangles and 1024. Grade 10s, it has been wonderful having you again, and I look forward to seeing you again next week. Goodbye.